Hi everyone, welcome back. Today we are going to do some review about the heap sort, and then we are going to see a little more about priority queue, and then we move on to the new chapter and we talk a little bit about the quick sort. Okay, so let's see the heap. So for the heap structure, and first remember it is a binary tree structure, and it is a nearly complete binary tree. So for the binary tree, and then we go move on, and how do we fill in the nodes? The rule is we want to fill in the nodes from top to bottom, and for each level or each layer we fill in the nodes from the left side to the right side, so we stop wherever we run after the nodes, and then we have a nearly complete binary tree structure. Okay, it's not the end of the definition of the heap. For the heap we have to maintain or satisfy a heap property, and that is, if you're talking about the max heap, and that is for the parent, it should be greater or equal to both of the children. Okay, so if we enforce this rule for all the parents and the children pairs, and then we have a max heap. So when we are saying it is a max heap, this means for the maximum, it's guaranteed to be on the top, or the maximum should be the root of the tree. Okay, and because a heap is a complete binary tree, and then the height of this heap should be log n. Okay, and a very quick question, true or false? Given a heap implemented using a one-base indexing array, a linear array, one-base indexing, and the children of the node with the index I will be 2i minus 1 and 2i. Is that correct or wrong? I'm giving you 5 seconds. 5, 4, 3, 2, 1. Okay, so true or false? The answer should be false. Why? Because we are using one-base indexing. And say if we just use the index 1 as example. So index 1, that's the root. So who are the children? 2 and 3, right? So 1 and 1, we have the children 2 and 3. So what are they? They are 2i and 2i plus 1. Okay, so it should be 2i and 2i plus 1. So let's move on, and we talk about heapify. So for the heapify is we want to maintain the heap property, and usually we want to call the heapify when the node I is wrong, and then we want to touch the node I, and when we are touching the node I, and then we are also visiting the two children, which are the L and R for the left and right. So what are we enforcing? We are enforcing the rule that the parent should be greater than or equal to both of the children. And what if this property is violated, and how do we fix it? So we have to swap which error is the largest to the parent, and then we pull the parent down by one level. And is that the end of the task? And the answer is probably no, because once we pull the parent down down by one level, and then the new location may still be not correct for this value. So what do? We have to further down and check whether the new location is the right location. And then we have to move down and we do the recursive calls until we pull one node down and down and down, and eventually we pull that down to a leaf, or it's not a leaf, but for the new location, the new children are both smaller or equal to the parent. And then we say, okay, we pull you down from here down here, and finally you are at the right location, right? Okay, and for the heapify, and remember the running time will be O log n. The worst case is we are putting one of the root all the way down to a leaf, and then how many moves are there? There are log n moves, right? Okay, and true or false? For one single heapify method call, we only guarantee that we got one value or one node is put to the right place. So I'm giving you 5 seconds. 5, 4, 3, 2, 1. So is that true or false? The answer should be true. Why? Because we are putting one node all the way down to the bottom. And probably there are more issues with this heap. But as long as we are putting, or we are touching a node and then pull it all the way down to the right location. What do we guarantee? We guarantee that, well, this node is at the right place, and probably there are even more nodes that we need to heapify or we need to fix. But doing one heapify, and remember that heapify is recursive, so it's guaranteed that for that node, it will be put at the right place. And next, we talk about build heap. So for the build heap, and remember, we don't have to do the heapify for all the values. Well, and for by the way, for the build heap, we start from where? We start from a list, a unsorted list of the values, and then when we are doing the heapify, we are doing the heapify to touch only the non-leaf values, right? So well, we are for the rest of them from the middle all the way to the end, and then they are leaves. So for the leaves, we don't have to heapify them because they are already leaves. They really don't have children. Okay, so when we are doing the heapify, we only use the when we are using the heapify, we only use the heapify to touch the non-leaf nodes. Okay, and okay, this is the build max heap. So we starting from in the middle, and then we go all the way down to 1. So this will guarantee that we can touch all the non-leaf nodes. Okay, so true or false? The second largest node in a max heap has to be one of the direct children of the root, given there are more than 4 values in the max heap. So is that true or false? So, okay, the answer should be true. Why? Because, well, if we have a value, and this value is the second largest, so what does that mean? This means this value is only smaller than the root, right? So if it is not one of the direct children of the root, this means between this node and the root, there is one more value between them. Well, is that possible? The answer is no. So in this case, well, we should know that if there is such a value, it is the second largest in the entire heap, and then this value has to be the direct children, one of the direct children of the root. Okay, so the next part we also talk about the build heap. Well, and when we just want to read the code, and you may feel that when we are doing the heapify, that is a log n algorithm, and then how many times we are calling the heapify when we are trying to build a heap, and the answer is we are calling the heapify for half n times, right? So we are repeating a log n function for half n of the time. So we feel that it should be a n log n method, but actually this is not a tightest bound. And if we want to do a tightest bound, and then well, there is a very smart proof that we can show this is actually a log n algorithm. This means if I give you a list of the random values, and then if I ask you to build a heap, and actually you can do that within a linear time. So this is kind of cool. So this means, well, you can build a heap and then have all of the values kind of sorted, not really 100% sorted, but at least we know the largest value are on the top, and the smaller values, they tend to be at the bottom, right? So this is the cool thing about the build heap. And the next part, we talk about the heap sort. So for the heap sort, there are really some of the cool things. Well, number one, this is an in-place sorting. Well, this means we don't have to ask additional memory space from the operating system, and this is important when you are sorting a big list of the values, right? And what is the strategy? The strategy is, first if we have a random list of the values, and then we want to do a build heap. So after we have the build heap, and then we know there is a heap build up, and then for the largest value, it is already at the very top. And then what do? And we are going to iterate from the length and down to the 2. And every time we are swapping the root with what? With the last leaf, right? We are swapping the root with the last leaf. And then, well, this means for the root or the largest value, we are keeping it at the end of the list. And then we do what? We want to reduce the size by 1. By reducing the size of the heap by 1, and then we are kicking the largest value from the heap. So we put that at the very end, and then we just do not consider the largest value as a member to the heap anymore. And then we want to do a heapify to make sure that the heap is fixed. And then we can move the second largest value, which is the new root, down to the leaf. So every time we remove the root and then we kick that out. So well, we do that and we repeat that for n-1 time, and then we will have this list sorted. And then if we are using a max heap, and every time we are moving the largest value to the end of the list, so we are sorting the list from low to high or high to low. The answer should be we are sorting this list from low to high. Why? Because we are, for each time we grab the largest value from the root and then we put it at the end of the list. So, well, the largest value will be kicked out first and then they will be at the end. So we sort this list from low to high. Okay? So, well, if we want to analyze the heap sort, and remember the first part we have on the line 1, we have a build max heap. For that, for this part, this is not a primitive step. This is actually a function cal, and this is a linear time algorithm. And after that, we are repeating the heapify for log n times. We are repeating a O log n algorithm, which is heapify for a total of n-1 times. So if we put them together, and then we will know this is a n log n algorithm. So is that the first n log n algorithm we have seen? The answer is no, right? Because we also have seen the merge sort, and for the merge sort, it is also a n log n algorithm. So if you want to compare the merge sort versus the heap sort, what is the cool thing about the heap sort? The cool thing about the heap sort is it is a sorting in place algorithm, right? Okay, so I'm going to stop this review part here, and the next video I'm going to move on and talk about the priority queues.